In Module 9, Section 2, we will look at factoring by special products. Remember the two special products that we saw in Module 5? They were the perfect square trinomial and a difference of squares. And these were the two formulas that we used. Whenever we had a binomial squared, it was expanded into the first term squared plus twice the product of two terms plus the second term squared. And if it was the difference of the two terms, the only thing that changed was the plus sign in the middle to a minus sign. Hopefully you also remember that we didn't have to use the special product formulas. We could have just FOILed instead. And the same is true here. We can just use the same factoring methods we've learned before to solve these problems. Let's try an example of finding out whether a polynomial is or is not a perfect square trinomial. So we want to decide whether 16x squared minus 8xy plus 2 plus y squared is a perfect square trinomial. The first thing I will do is write the corresponding equation from the last slide. So because this has a minus sign, we would use a squared minus 2ab plus b squared. So we want to see if our polynomial matches this form. In order for that to be true, the first term has to be a perfect square, which means it has two identical factors. Well, we know that we can get 16 by multiplying 4 and 4, and x squared is x times x. So we could actually rewrite 16x squared as 4x squared. So 4x and a would be the same. The last term, y squared, can break up into y times y. It already looks like something in the squared form. So y is just taking the place of b. The trickiest part is making sure that the middle term is correct. And so we want negative 8xy to be the same thing as negative 2 times the first term times the third term. And so we take negative 2 times 4x, because that took the place of a, times y, because that took the place of b, and that gives us negative 8xy, which is exactly what we see in the middle. So the answer here is yes. This is a perfect square trinomial. Now that we've gone through to determine how to find out whether a polynomial is or is not a perfect square trinomial, we're going to more or less abandon the perfect square trinomial factoring method and just use the same factoring techniques that we have seen in previous sections. So using the same steps from Module 9, Section 1, we first want to find whether or not the polynomial has a GCF. And in this case, the GCF is 1, so we just write no GCF, or at least no GCF to speak of. Secondly, we multiply the coefficients from the first and the last term. This y squared has a coefficient of 1. So 16 times 1 is 16. We want two numbers that multiply to 16, but that add to the middle term, which is negative 8. Because we have a positive product with a negative sum, our two factors will be negative. We can find that negative 4 times negative 4 is positive 16, but negative 4 plus negative 4 is negative 8. So this is the pair of factors we want to use. We then take these two factors and put them into the original polynomial in place of the middle term, using the same variable the middle term had. So this becomes 16x squared minus 4xy minus 4xy plus y squared. At this point, we factor by grouping. Group the first two terms, group the last two terms. In the first group, the first two terms have a common factor of 4x. And if we factor out of 4x, we're left with 4x minus y. In the second group, 4xy and y squared have a common factor of y. But because the leading term, the first term in the group, is negative, we're going to factor a negative y. And when we do so, we are left with a positive 4x minus y. We now have a 4x minus y in common in the first and last term. So we write that binomial once, 4x minus y. And then we write the remaining polynomial, which will also be 4x minus y. So another way we can write this, because we have two identical polynomials, is 4x minus y squared. Let's try another example. X squared plus 12x plus 36. Again, we go through the process of trying to find the greatest common factor, and there's not one other than 1, so we say no GCF. Now, because we don't have a coefficient, a coefficient that's not 1 in front of x squared, we don't have to go through the entire factoring by grouping process. We know that x squared can only be factored into x times x. And so we can look only at the last number. Now this only works when we have a coefficient of 1 in front of x squared. If that would have been a 5 or a 7 or something that we couldn't factor out, then we would have to go through the entire factoring by grouping method. Instead, we look at just 36, and we want two numbers that multiply to give us 36, but that add to give us 12. And those two numbers will be 6 and 6. So because our coefficient of x squared was 1, we can just simply put these numbers into the binomials, into the missing places. So this becomes x plus 6 times x plus 6, or x plus 6 squared. In the next example, we want to factor 4m to the fourth minus 4m squared plus 1. Again, we try to factor a GCF. We don't have one other than the number 1, so we say no GCF. Here, because we have a coefficient in front of our leading term, we have to go through the factoring by grouping method. So we multiply the first and last coefficients, that gives us 4. So now we want two numbers that multiply to give us 4, but that add to the middle term, negative 4. And those two factors will be negative 2 and negative 2. We replace the middle term with these two factors. Remember, they get the same variable that the middle term started with. So this becomes 4m to the fourth minus 2m squared minus 2m squared plus 1. We group the first two terms together, group the second two terms together. In the first group, the GCF is 2m squared. And when we factor out 2m squared, that leaves us with 2m squared minus 1. In the second group, they have nothing in common, but because the leading term, the first term in this particular group, is negative, we're going to factor out a negative 1. So when we factor out negative 1, we're left with a positive 2m squared minus 1. We now see we have a common binomial. When we factor out the binomial, we write it first, 2m squared minus 1, and then the resulting polynomial, which will also be 2m squared minus 1. So we could rewrite this as 2m squared minus 1 to the second power. Let's try another example, 25x squared plus 50x plus 9. We look for a GCF, we don't find one, so we say no GCF. We then go straight to multiplying the first and last coefficients. 25 times 9 is 225. So we're looking for two numbers that multiply to give us 225, but that add together to give us a positive 50. And so with larger numbers, we still go through the same process that we would any other time. We can use a few tricks. Because 225 ends with the number 5, we know it's divisible by 5. So we take 5 times, and 225 is divided by 5 45 times. So 5 times 45 is 225. 5 plus 45 also happens to be 50. So those would be the two factors we want to use. We put those in place of the middle term in the original polynomial. We now have 25x squared plus 5x plus 45x plus 9. We group the first two terms, group the last two terms. The GCF in our first group is 5x. The resulting polynomial is 5x plus 1. In the second group, the GCF is 9. And the resulting polynomial is 5x plus 1. So we have a binomial factor in common. When we factor out the binomial factor, we have 5x plus 1 times the resulting polynomial is 5x plus 9. Now in this case, this is not a perfect square trinomial. We do not have two identical factors, so don't try to write this with an exponent of 2. Let's try another example, 3n squared minus 6n plus 3. We try to factor the GCF, and in this case, we do have a GCF. The GCF here is 3. So our first step, we factor out 3, and that leaves us with n squared minus 2n plus 1. Now, because the coefficient of n squared is 1, we can go ahead and break this up into two sets of parentheses. N squared becomes n and n, so we're just looking for the missing pieces. We look at the constant at the end of our trinomial and the middle coefficient. We want two numbers that will multiply to give us 1, but that will add to give us negative 2. Well, the only way we can get 1 is positive 1 times positive 1, or negative 1 times negative 1. If we make both factors negative, they add up to a -2. So in the missing blanks in the binomials, we put a -1 and a -1, and we were finished. Another way we could write this is 3 times n minus 1 squared. That would be okay as well. Let's now look at that second special product that we saw back in Module 5. And that was a difference of 2 squares. We know that we have a difference of 2 squares if both terms are perfect squares and the signs of the terms are different. And so we will never have the sum of 2 squares. That's something that's factorable with real numbers. So here's an example, 9x squared minus 25y squared. We're not going to factor this yet, but let's just look at how we have 2 different squares. We say that something is a perfect square if it can be rewritten as 1 factor raised to the 2nd power. And so in this case, our x is raised to the 2nd power, but 9 is just 9. We would rewrite 9 as 3 times 3, or 3 squared. So we have 3 squared x squared, which is the same thing as just 3x to the 2nd power. Following the same pattern, 25 is 5 squared, so 5 squared y squared, or just 5y squared. And that will always be our first step before we try to factor something in this form. Once we have something written as a term to the 2nd power minus a term to the 2nd power, we take those terms and fill in the blanks in our binomial. We add those terms in the first binomial and we subtract those terms in the second binomial. So let's try an example. Here we want to factor x squared minus 9. We have 2 terms. There's a minus sign in between them, so it's possible that this will be a difference of 2 squares. The first term is already written as something raised to the 2nd power, x raised to the 2nd power. 9 can be rewritten as 3 raised to the 2nd power. So x takes the place of a in our formula, 3 takes the place of b. And remember, the formula said a squared minus b squared equals a plus b times a minus b. So we fill in the right side of the formula, and that gives us a, or x, minus plus 3. So we put a plus. A takes the place of x. 3 takes the place of b. X plus 3, x minus 3. Let's try another example. Y squared minus 16 over 25. Again, y squared, it's already in the form of a term raised to the 2nd power. And with a fraction, really we just need to find the top number raised to the 2nd power. The bottom number is something raised to the 2nd power. 16 can be rewritten as 4 squared. 25 can be rewritten as 5 squared. So the whole thing, we would say, is 4/5 squared. Filling in our formula from before, a squared minus b squared equals a plus b, so y plus 4/5 times a minus b, y minus 4/5. Let's try some more examples. Here we want to factor 4x squared minus 1. In the first term, the x is squared. We need to rewrite 4. 4 is 2 times 2, or 2 squared. So this would look like 2x to the 2nd power, which is the same thing as 4x squared, minus, well, 1 is the same thing as 1 times 1, or 1 times 1 times 1, as many 1s as we need. So let's just say 1 is the same thing as 1 squared. Now that we have the correct form, we fill in the binomials. We use the 2x and the 1 both times. The first binomial, we are adding. The second binomial, we are subtracting. We use the same exact process when each term has a variable. Here we have 36a squared minus 49b squared. 36 is 6 times 6, so we can rewrite the first term as 6a to the 2nd power. The second term, 49 is 7 times 7, so 7b to the 2nd power. Filling in our binomials, we use the 6a and the 7b. In the first set of parentheses, we are adding. In the second set of parentheses, we are subtracting. Now, in this example, we have to go one extra step before we have a difference of squares. We have 4x cubed minus 49x. The first step, and we should really try this every time, but we need to factor out the GCF. The GCF here is x. When we factor out an x, we are left with 4x squared minus 49. Let's now put our two terms in parentheses in the correct form, where it's a number or a term raised to the second power. So this becomes 4 is 2 times 2, or 2 squared. So this becomes 2x to the second power minus 49 is 7 times 7. So 7 to the second power. Our resulting polynomial then breaks down into two binomials. The 2x shows up as the first term in each binomial, 7 as the second term. In the first binomial we add, and the second binomial we subtract. Let's try it when the constant is in front and the variable is at the end. Here we have 49 minus x squared. Do not try to rearrange these. Okay, we cannot flip our terms when there is a minus sign involved. Otherwise, it's going to give us something very bad. So we start by just rewriting in the form that we want. 49 is 7 squared. X squared is just x squared. This now breaks down into two binomials. 7 takes the first term in each binomial. X takes the second term in each binomial. In the first binomial, we add, and the second binomial, we subtract. In this example, we will have to factor the greatest common factor again before we have a difference of squares. So first we factor the GCF, and when we do, we find that the GCF is 3. So we factor out a 3 from both terms. 75 divided by 3 is 25. So this becomes 25r squared minus 9. We then rewrite it in the form we want, where we have the first term squared and the last term as a something squared. 25 is 5 times 5, so we can rewrite this as 5r to the second power. 9 is 3 squared, so 3 to the second power. Now that we have the correct form, this will factor into two binomials. 5r takes the place of the first term each time. 3 takes the place of the second term each time. In the first set of parentheses, we add. In the second set of parentheses, we subtract.